Hello, good day to all. My name is Chandrasekhar and I intend to cover the entire spectrum of class 11 and class 12 physics through these video lectures, and this is just going to be the start of it. In this video, I'm going to talk about first chapter of class 12, namely electric charges and field. As you can see, the weightage marks allotted mainly for Karnataka second PUC students is about 8 marks. Out of 8 marks, one usually gets one long answer question in the derivation section or one numerical problem. And for other competitive exams such as JEE, NEET and KSET are concerned, in JEE it was seen that in 2019 various papers there was at least one question from this chapter, while in NEET there were 2 questions, and while in KCET there was one question. Now let us take a look at what are the prerequisites in understanding and studying this chapter. The prerequisites are vectors from your class 11 of first PUC and Newton's laws. I request students to have a revision of these 2 topics because we will be utilizing them extensively throughout this basic chapter. The reference books are, as usual, NCERT Class 12, Volume 1, NCERT Exemplar, and this is another book. These are a couple of books that I would suggest all students to go through. Namely, first one is by Sears and Zimansky, and it is called University Physics. The next book is quite popular among all the Indian students, H.C. Verma, Volume 2, and we'll be majorly utilizing these 2 books for solving problems. And of course, we will also take a look at previous question papers of PUC exam, CET, NEET, as well as JEE. Without any delay, let's just get into the chapter. As the name suggests, it's electric charges and field. Let us take a look what electric charge is all about. As you can see, electric charge is something possessed by material objects due to which electrical and other related effects are produced. The concept of charge was already known to people since the times of Greek philosophers. People knew that when you take a comb or when you took an amber and if you rubbed it with wool, it started attracting bits of straw, right? It's a common experience for each one of us that when we take a comb and when we rub it, when we comb our hair, and it is seen that the comb actually attracts pieces of paper. Now, how do you produce these charges? Electric charges are basically produced by disturbing the neutrality of an atom. It was an American scientist, namely Benjamin Franklin, who discovered that there are 2 types of charges, namely positive and negative. Now, how do you get a charge? How do you produce charge? That is, methods of charging. The methods of charging are basically involving 2 types. The first type is by charging by friction. Charging by friction, it involves rubbing bodies physically. Example, like we've already remarked, when a glass rod is rubbed with silk, negative charge appears on silk and positive charge appears on glass rod. Now, what has happened here? This is basically you have disturbed the neutrality of an atom. Atom in general is supposed to be neutral, meaning that there are equal number of protons as well as equal number of electrons, right? There is an equal positive and negative charge. It is balanced. Now, when you try to rub a glass rod with silk, it is found that there is a negative charge appearing on silk, meaning that silk is gaining electrons. Silk is gaining electrons. While glass rod appears to be positively charged, meaning that it is losing electrons. Right? So one of the things about charging by friction involves one of the substance gains electrons and while the other substance loses electrons. An equal number of electrons are lost and equal number of electrons are gained, right? Now, appearance of this positive or negative charge on substances depends upon a parameter called work function. Body with higher value of work function becomes negatively charged by gaining electrons. One with lower work function becomes positively charged by losing electrons. Now, this is the first method. The second method of charging is by something called as charging by induction. A body is charged by putting it in contact with another body, either directly or by means of conductor. Now, what do we mean by this? Now, let us consider a case 1 where we have a sphere 1 which is charged rather, and sphere 2 which is uncharged. Now, what we have here is we have taken a copper wire. Let's say sphere 1 has charged X amount of it, right? When you connect sphere 1 and sphere 2 with a copper wire, it is found that both spheres, because both spheres are identical here, it is found that this sphere 1 gets a charge of X by 2, while the other sphere also gets X by 2. By means of conductor, when you connect two spheres, it is found that charge transfers from one of the sphere to the other spheres. So this is one of the method of charging by induction. And this is basically one of the methods which involves direct contact. In fact, one can also charge two spheres without actually connecting them without a piece of conductor or a copper wire. The second method involves, this is the case 2. Now I've taken a glass rod, and this glass rod is having a negative charge. Initially, the sphere is uncharged. Initially, please remember that sphere is uncharged. And when this glass rod is brought near the uncharged sphere, now as you know that this sphere is neutral. And what does it consist of? It consists of protons as well as electrons. Because the glass rod is negatively charged, it tries to push all the negative charge present inside the sphere to the other end. See, as seen here, the negative charge here has gone to the other end. So what happens to this end of the sphere? It becomes positively charged, right? It becomes positively charged. And what about the other end? It becomes negatively charged. So as we can see here, without any actual contact, one is able to charge the sphere by bringing a charged substance near an uncharged substance, right? Now the third case is considered where one of the ends of the sphere is grounded. When you ground a sphere, what happens is the negative charge starts flowing to the ground while the positive charge remains. So as you can see in this method of charging, that is by charging by induction, you can actually get two bodies charged by putting them in contact, right? By putting them in contact, this is the case 1. Or without contact itself, you can establish a charge on a substance, right? Without actual contact, right? I'm sorry about that, without actual contact, right? Now moving on, as we can see, this is about methods of charging. It's a very important question from the perspective of your second PUC exam. It's usually asked for 2 marks. What are the methods of charging? And as you can see here, it's charging by friction, that is, which involves bodies, which involves you have to rub two bodies physically. And the second method is obviously by putting them in direct contact, or in indirect contact, or without any contact itself, you can establish charging. Now moving on, what are the basic properties of charge? The first property that I would like to discuss is called quantization of charge. And it is found that charge is always quantized and always appears as integral multiples of elementary charges. The elementary charge is well known to every one of us. It is about 1.6 into 10 to the power of minus 19 Coulomb. Coulomb is basically an SI unit of charge. We will get to what Coulomb is. But please remember that the least amount of charge that is possible in the universe is about 1.6 into 10 to the power of minus 19 Coulomb. The subsequent charges can only take integral multiples of this elementary charge, that is q is equal to plus or minus ne, where n is equal to 1, 2, 3 and so on. You cannot have 2.5e. 2.5e is not possible, while you can have 2e, right? Now, this fact was first suggested by Faraday in his laws of electrolysis, while the experimental verification to basic quantization of charge was due to Millikan in 1912 in his famous oil drop experiment. So, repeating, charge is quantized and it always appears as integral multiples of elementary charge. The second property that I would like to discuss about the properties of charge is charges follow scalar law of addition, meaning they always add like real numbers. What do we mean by that? Let's say if you have two charges, plus 2q and minus 3q, then total charge would be just plus 2q minus 3q, which is nothing but minus q. So in a sense, they don't add like vectors, they're just adding like real numbers, right? So which suggests that charge is a scalar quantity, obviously, right? The third important property about the charge that I would like to talk about is charge is conserved, meaning algebraic sum of positive and negative charge in an isolated system always remains constant. Well, you can talk about charge conservation, which means that you can create charge and you can destroy charge, but this only happens in pairs, right? What I mean to say is, for every positive charge created or destroyed, a subsequent negative charge is also created or destroyed. One can see this happening in a phenomenon called pair production. Pair production is a phenomenon where a gamma ray photon, this is a photon, it materializes into something called as a positron and an electron. This is called positron and electron. So clearly, the three most important basic properties of charge are: the first one, charge is quantized; second one, charges follow scalar law of addition, meaning they add like real numbers; third one, charge is conserved, meaning algebraic sum of positive and negative charge in an isolated system always remains constant. The fourth most important property, of course, is charges cannot exist without mass. If you want a charge to exist, then it must have mass. A substance must have mass. But what about the other way around? Mass can, of course, exist without a charge, but not the other way around. Charges always require mass to exist. And the fifth important property is, which is already known to every one of you, that is, like charges repel and unlike charges attract. Now moving on, the next concept is about Coulombs law. What is Coulombs law? Coulombs law is basically a quantitative statement about force of interaction between 2-point charges at rest. Now take a look at this word point charge. The point charge is a finite amount of charge contained in a body whose physical dimensions are negligible. It is as if like you're packing a charge into a substance whose volume or whose physical dimensions are not so important. It's just like a point that you deal in geometry. Now, what does this Coulombs law say? The statement of Coulombs law states force of attraction or repulsion between 2-point charges at rest in vacuum. Please note that the words force of attraction or repulsion between 2-point charges at rest in vacuum is directly proportional to product of the magnitude of charges and inversely proportional to square of the distance between them. Now let us take word by word of the statement. It states that if you have 2 point charges, let's say Q1 and Q2, which are at rest, and they are separated by a distance r in a vacuum, and obviously Q1 and Q2 both are at rest. According to Coulombs law, the force of attraction or repulsion between two charges is given by the product of magnitude of two charges, that is the product of magnitude of two charges, and is inversely proportional to square of the distance between them. As you can see, Coulombs law is quite reminiscent of Newton's law of gravitation, which you've already studied in class 11. The expression for Newton's law of gravitation was as follows: F is equal to g m1 m2 by r square, right? So in a sense, Coulomb's law is pretty much similar to the universal law of gravitation, but with slight changes here. In place of masses, what do we have? We have charges, right? In place of gravitational constant, we introduce another proportionality constant in Coulomb's law, and it is given by, and rather it is read out as 1 by 4 pi epsilon naught q1 q2 by r square. As you can see, this 1 by 4 pi epsilon naught is just a proportionality constant, and epsilon naught here is called permittivity of free space. What is it called? It's called permittivity of free space, and value of epsilon naught in SI system is given by 8.854 into 10 power minus 12 Coulomb square per Newton per meter square. And the value of 1 by 4 pi epsilon naught is taken as 9 into 10 power 9 Newton meter square per Coulomb square. It is very important to remember these quantities, especially 1 by 4 pi epsilon naught, because we'll be solving most of the problems using Coulombs law. Now let us take a look about the important points about Coulombs law. First point, interaction between two charges at rest is referred as electrostatic or Coulombic interaction. It is very important to remember that the interaction, whenever you have two charges at rest, the forces exerted between them is usually called as electrostatic or Coulombic interaction. Electrostatic, as you can see, the word electrostatic means that two charges are at rest and they're exerting forces on each other. Because the forces are governed by Coulomb's law, therefore it is called as Coulombic interaction. Also notice that Coulombic interaction is a two-body interaction and is not affected by presence or absence of other charges. This is quite similar to universal law of gravitation or the force of interaction between two masses. The force of attraction between two masses is also not affected by presence or absence of other masses. Similarly, Coulombic interaction is also not affected by presence or absence of other charges. Third important point is electrostatic force depends on medium, and Coulomb's law expression is to be modified if charges are in some kind of medium, say water. Just take a look at the statement. The statement says in vacuum. So therefore, it is very important to modify Coulomb's law statement if you are using this expression 1 or 2 rather, equation 2, if you have to use it in a material medium. Let's say, like for example, that we have taken here is water. And accordingly, the expression is modified as F is equal to 1 by 4 pi epsilon. Remember, previously, in case of vacuum, we had chosen it as epsilon naught. Right now, we are taking it as epsilon. And this epsilon, we are going to call it as permittivity of medium. Fourth important point that we are going to discuss here is a useful ratio called dielectric constant or relative permittivity. the symbols used are K or epsilon R is defined as epsilon R is equal to epsilon by epsilon naught. That is the ratio of permittivity of medium to that of permittivity of free space. More about this we'll study in the next chapter. Right. Because the forces of interaction and in general the forces are of vector in nature, vectorial in nature, it is very important to discuss Coulombs law in vector form. And this is a very important question as well from the point of view of your board exam, and it is usually asked for 3 marks. What have I taken here? I have taken two charges Q1 and Q2 at positions A and B with reference to origin, some fixed origin O. Here R1 and R2 are two position vectors with respect to the coordinate system that I have chosen. And from triangle law of addition, one can see that the relative separation between A and B is given by vector R21, which is equal to R1 minus R2. And we shall use Coulombs law. And according to Coulombs law, if you see that charge Q1 exerts a force on charge Q2 and charge Q2 exerts a force on charge Q1, therefore one may write the force F21 exerted by charge Q1 on Q2 as F21, which is equal to 1 by 4 pi epsilon naught Q1 Q2 by R21 square multiplied with R cap 21, where R cap 21 is a unit vector extending from 2 to 1, from B to A. Similarly, one can write F12, which is 1 by 4 pi epsilon naught Q1 Q2 by R12 square R12 cap. Now we have R cap 12, which is basically a unit vector in the direction of 1 to 2. So clearly from equations or expressions rather 3 and 4, we see that F21 is equal to F minus of F12. So one sees that the forces exerted by charges on each other are equal in magnitude and opposite in direction, which talks about the validity of Newton's third law. So that leaves us to an important conclusion, that is, electrostatic forces always act in pairs, meaning action and reaction. The second important conclusion is a comparison with gravitational force reveals that electrostatic force is about 10 to the power of 36 times stronger than gravitational force. Third important point that I would like to talk about is Newton's law of gravitation is universal. However, Coulomb's law is not universal. What does this imply? It just implies that Coulomb's law keeps changing and it depends upon medium rather. It just depends upon the medium. While Newton's law of gravitation is same everywhere. The force of attraction between two masses is always gm1 m2 by r square. The proportionality constant in case of Newton's law of gravitation is g, which is a universal gravitational constant, and it is same across all the universe. However, the proportionality constant 1 by 4 pi epsilon changes with respect to medium. Therefore, Coulomb's law is not universal in nature. Now let's come to the next important concept, that is basically the units of charge and definition of 1 coulomb. As already remarked while talking about basic properties of charge, the SI unit of charge is coulomb, and the definition of 1 coulomb is made by using the expression of Coulomb's law. So here Q1 and Q2 will be equal to 1 coulomb when R is equal to 1 meter and F is equal to, from here we've already taken it to be 9 into 10 power 9. So obviously let me read out the definition for you. So using the expression of Coulomb's law, 1 coulomb is that charge which when placed at rest in vacuum at a distance of 1 meter from an equal and similar charge at rest repels it with force of 9 into 10 power 9 Newton. This question is asked a lot of times as a one marker, or probably a question may be asked in this way: state Coulombs law and define 1 coulomb. It can be asked as a 3-mark question, or it can be asked as a 2-mark question, depending upon the weightage, right? So this is all about Coulombs law. An addition to Coulombs law is made by considering the concept of superposition principle. What is the superposition principle all about? It helps us to determine the net force when multiple charges are present. What do you mean by multiple? That is more than 2 charges. So far, we've been restricting ourselves in Coulombs law by just considering 2 charges at rest. Now there arises another important question. What happens if we have more than 2 charges? That's where the concept of superposition principle comes into picture. According to superposition principle, when a number of charges are interacting, total force on a given charge is a vector sum of all individual forces on the given charge by all the other charges. What does this mean? Take a look here. I've considered 3 charges here. It can be extended to n charges as well, but for simplicity, I've taken only 3 charges: Q1, Q1, Q2, and Q3. Now, if I have to use superposition principle and if I have to find what is the net force on this charge Q1, according to superposition principle, F net is going to be the vector sum of force exerted by Q2 on Q1 and force exerted by Q3 on Q1, which is what I have written here. Similarly, if I have to find what is the force exerted on Q3, what is the net force on Q3 on this particular charge, this is going to be the force exerted by Q1 on Q3 and force exerted by Q2 on Q3, which is basically F31 plus F23. Similarly, on Q2 is going to be F12 plus F23. So from above expressions, we see that force between any 2 charges is not affected by presence or absence of other charges. What does this mean? If you take a look at the net force on Q1, we see that the net force on Q1 is basically, one second, just a minute. The net force on Q1 is basically force due to Q2 on Q1 and force due to Q3 on Q1. And it does not get affected by the force here. This another force, there is another force between Q3 and Q2. So obviously, this leads to a very important conclusion that Coulombs law interaction or electrostatic interaction is a 2-body interaction. And therefore, it is very, very important to remember the statement that electrostatic forces are always 2-body interaction. And they are not affected by presence or absence of any other charges. Second very, very important concept to remember is a convention. Force exerted by positive charge is outward in nature. This is the direction of force if you take a positive charge. And by negative charge is towards it. It's towards the negative charge. This concept is extremely important. I just cannot overemphasize the fact that this is so important that we will be utilizing this concept throughout in our problem solving journey. Right. So above convention, along with Coulombs law and superposition